is now supposed to remind you of things that you should already know and have a good understanding of going into this chapter. And this has to do with how we interpret models. So remember that if we're using the balls and sticks and that the colored balls, we have some information in there as well. Red is usually for what? Red is not for hydrogen. Red is usually for oxygen. The white is usually for hydrogen, sometimes yellow. If it's black, that would be what? Carbon. So you have to look at these models now and interpret what the model is telling us. This model is telling us that we have a molecule of H2O2. Now, you don't know what that is yet. Turns out this is hydrogen peroxide. But the important point here is that our model represents that for every molecule of hydrogen peroxide, we have 2 atoms of hydrogen and 2 atoms of oxygen. That's what the subscript is telling us. Now, we learned from the theories and laws from Proust and Dalton that these atoms are going to combine in small whole number ratios to make these compounds, these molecules. So we already knew that. And pretty soon, we're going to be looking at some reactions. And later on in the class, we're going to learn about how we describe those reactions with another kind of model or shorthand called the molecular equation or chemical equation. And we're going to show that hydrogen peroxide here is going to break down into 2 different molecules. And from the model, you can see what those are. What's this one here? This is oxygen, O2. Oxygen, it turns out, when it's by itself in nature, actually is most stable as a diatomic molecule. There's 2 atoms of oxygen that are bonded to each other. And we'll be looking into that in more detail later on in the class. This has 1 molecule of oxygen, sorry, 1 atom of oxygen and 2 atoms of hydrogen in it, H2O, that's water. So from a diagram, from our model, we have a chemical reaction. We can write that up on top that we have some reactants here on the left-hand side. Hydrogen peroxide is going to decompose into the 2 molecules, H2O and molecular oxygen. And we can tell from the subscripts what the ratio of atoms are in those compounds. Now, later on, we're going to learn about how to make sure that we obey the law of conservation of mass. Who knows what the law of conservation of mass is? Energy cannot be created or destroyed. Matter cannot be created or destroyed. That's essentially saying the same thing. If it can't be created or destroyed, that means you need to have the same number of atoms on the left-hand side of the equation as you have on the right-hand side of the equation. Okay? So everything that we're going to do in this class, and if you continue along next semester, of all the reactions, we have to obey. You must obey the law of conservation of mass and energy. In a chemical reaction, you can't create or destroy matter. You can't create or destroy energy. So we handle that in this case with using coefficients in front of each material. In order to obey the law of conservation of mass, in this case, we need to react 2 molecules of hydrogen peroxide, and that will then produce, when it decomposes, 2 molecules of H2O and 1 molecule of molecular oxygen. Now, don't worry about that balancing act. We'll be doing plenty of that in due course when we get to probably chapter 7, actually. So that doesn't come until much later in the semester. So I wanted to get you in the mindset now of simply using these coefficients in front. This is the number of molecules, right? We have 2 hydrogen peroxides. That's going to produce 2 of these and 1 of these. And if you count up the atoms, either in the picture or in my chemical formula here, chemical equation, you'll see that we are obeying the law of conservation of mass. And you can see that in picture form as well. So again, that's just getting used to looking at these models. In this case, the models are just pictures. We have reactants on the left, and we have products on the right, and we have the same number of atoms. They've just recombined. They've changed partners. We've broken chemical bonds, and we've made new chemical bonds. Love it. All right, so for those of you who have watched the video now, your notes should look like this, just like mine. Of course, this I think is from the video, so that's what it should look like. So you know about electrons, protons, and neutrons, various definitions. You will be held accountable for knowing the information that's in those videos, even if I haven't expressly talked about it here in lecture, right? It's part of the classroom, it's part of the learning. I then talk a little bit about isotopes and ions. Right? So change the number of protons, that defines the element. Okay? So if a different number of neutrons means that you've changed the element. If you have a different number of neutrons, but the protons stay the same, then we have what's called an isotope of that element. Most elements have multiple isotopes, meaning that they're all the same element, right? And the example I showed in the video is for carbon. 3 isotopes of carbon, carbon 12, carbon 13, and carbon 14. They're all carbon because they all have 6 protons, but they each have a different number of neutrons, so they have a different mass number. And some of them, sometimes isotopes are radioactive, sometimes they're not. Unfortunately, we won't be talking much about radioactivity in this class. It's a fun subject, but I might be able to touch upon it here or there for you as it comes up. We also have a case that we'll be seeing starting this chapter and moving on into chapters 3 and beyond, that you can have a different number of electrons relative to the number of protons. That's going to give you a different ion. All right, so I want you to learn this right now. Okay, we'll practice it, and then every morning you wake up, I want you to go through this mantra here. Okay, you change the number of protons, you change the element. You change the number of neutrons, you're changing the isotope. You change the number of electrons, you're changing the ion and the charge. It's like what? It gets finer. Not necessarily. The comment was it gets finer and finer every time. Not necessarily. It's just these are what happens when you change the 3 main components of the atom: the electrons, the protons, and the neutrons. Okay, so now let's go back to our model building, the scientific method that we talked about before, and the ways that we then use models to understand more and more about how the atom is actually structured. So let me start by reminding you of where we left off here. So from chapter 1, we talked about the experiments of Proust and from Dalton. And Dalton's work, this was around 1803. Remember, this is not a history class, but I like putting things into historical context for you. From this work, we came up with the first model of how an atom is structured. In fact, the first idea of what these things were. This is the atom, comes from the Greek atomos, which means to not cut. And Dalton's model of the atom was simply that, something that can't be divided any further. It can't be cut further. Here, let's show my artistic prowess here. Let's just show some sphere here. This is just some shading. Not much of an artist today. Here, let's put some depth to it here and there. Some 3 dimensions to it, all right? So Dalton's model of the atom was just this thing, this amorphous sphere that had some physical and chemical properties that were unique to each element, and you couldn't cut it any smaller. The fundamental unit was the atom. But they didn't know at the time about protons and neutrons and electrons, no charges. This was neutral, right? Elements in nature are neutral, they're not charged. So that was the model. And that model lasted for pretty much like 100 years until the next set of experiments came along that required some change to that model using the scientific method. So this is almost 100 years later now. And in particular, we're talking about the work of J.J. Thomson. And we'll also be talking about the work of Robert Millikan on this slide. Now, in particular, J.J. Thomson's experiment used, this was back in about 1897. So like I said, about 100 years later. And he was using, or his laboratory was using something called cathode ray tubes. Does anyone know what a cathode ray tube is? You do. What's a cathode ray tube?
CRT, it utilizes the magnetic field to basically force things to go one way or the other. It's actually what my oscilloscope uses.
Okay, so that was a very detailed explanation of the CRT. Sometimes I ask this question and the answer is like, oh yeah, my grandma's TV set, that's a CRT. And it is. The old-fashioned television sets. Remember, they're big and bulky. You probably don't remember because you grew up in the age of flat screen TV. Completely different technology now. But the cathode ray tube is something that's evacuated, and then using magnetic or electronic fields, you can change the trajectory of these charged particles, and they hit a phosphorescent screen in different places. And then depending on the nature of that phosphorescent screen, you get something lit up. So he said that your oscilloscope uses a CRT, and they do. And oscilloscopes usually are like green, fluorescent green. That's some particle beam is hitting the fluorescent screen or phosphorescent screen, causing it to light up. Back in the Stone Ages, computers had monochromatic screens. So they were either yellow, orange or green, same kind of idea. Now, of course, we have much more modern technology. But the CRT, the cathode ray tube, that's exactly what this is here. So does it say cathode ray tube anywhere on this slide? Probably not. So let's just put it up here. CRT, cathode ray tubes. And it's just as I described, right? It's an evacuated tube. It has some phosphorescent coating. And what Thomson was able to do is take a battery and hook up the poles of the battery to what we call a cathode and an anode. Don't worry about that now, what those names are. The positive end and the negative end, okay? And in the anode, if you can see here on this slide, there's a little hole there in the anode. And what they were able to do was demonstrate that when you hook a battery up to the poles and separate them like this in a vacuum, you can actually find that there's some invisible particle. And I'm just going to draw it as a dashed line here. They couldn't see the particle being emitted there, but they can see the effect of it because when it hit, it was some energetic particle. And when it hit the phosphorescent screen, it glowed. So magically, they hook up the battery in this kind of an apparatus and they can see something's glowing on the other side. So somehow they made a particle out of nothing. Not only that, they can get that little phosphorescent spot to move, either using a magnetic field. So here we're using magnets. The North Pole is usually considered to be positive and the South Pole is normally considered to be negative. Or they found that if they just put in an electric field, they could also deflect the trajectory of these particles. Because it was always deflected towards the positive, that meant that whatever these particles were that they were forming, these particles had a negative charge. And they called these particles electrons. This is the first experiment that had some scientific evidence that there was something in this neutral atom that when they put it under this situation, they can actually get a negatively charged energetic particle coming out. And they detect it and they can manipulate it. So they know things about this particle, this electron. They know that it's negatively charged. And in fact, by adjusting both the magnetic and electric fields at the same time, magnetic and electric fields at the same time, they can actually balance the effect that each one had. And in that balance, they can then calculate what we call the mass to charge ratio. Because they do have a charge. We know it's a charge because we can deflect it towards the positive, and we know that opposites attract. And they are imagining that there's a mass here because they formed some particle that does something. So scientists tend to think of that as something has mass that can be able to do that. And they can actually calculate this mass to charge ratio. All that means is that they know that if you take some mass and you divide it by some charge, let's call that E, you come up with a number. And that number is always the same. In this case, the number is negative, remember these are negatively charged, negative 5.69 times 10 to the minus 12th kilograms per coulomb. So that capital C, that's the unit coulomb. Now, there's going to be a lot of numbers that you're going to see in this class that we're going to use in computation. Don't worry, we're not going to be using this number. We're not going to be working in coulombs at all. In fact, if you recall from the half of you that watched the video, right, the charge of an electron here, we actually do measure in coulombs. But that's too inconvenient for us to use. So instead, that number of coulombs, we're just going to assign a relative 1 to it. So the charge of an electron is negative 1.6 times 10 to the minus 19 coulombs. We're just going to call that 1 minus. The charge of a proton, which is the equal magnitude but opposite in sign, it's the same value in coulombs, but now we're just going to assign that a 1 plus. But this number is even different. That's not the same number that's in the table. That's because this is the mass to charge ratio. It's not just the mass, and it's not just the charge. This is what Thomson was able to calculate, but they could not determine what the mass or the charge was separately. All they could determine was the ratio. So let's put that in here, but couldn't measure mass and charge separately. For that, we needed another experiment that came along, around 10 or 20 years later, and that was the work of Millikan using this contraption. I'm not going to spend too much time describing it. You can read about this in the textbook. Right, this is Millikan. Millikan actually won the Nobel Prize for this work. Not that the Nobel Prize is anything special. Lots of smart people go into science, but I do like to point out sometimes when their contribution to science has been noted in this way. This was in 1923 when he won the Nobel Prize. Again, I'm not going to test you on that date. So what Millikan was able to do was take these oil drops, take oil and make oil drops using, it's funny that we call this an atomizer. This does not make atoms, right, in the sense that we're talking about atoms. This is like a perfume atomizer, right? It's just making a small mist. You're making very, very small oil droplets. And then you make those oil droplets, you drop them by gravity. You don't drop them by gravity. It takes them through this little hole that's in this device. And then in that hole, you bombard them with X-rays. And by bombarding them with X-rays, you give them a charge. So now we have charged oil droplets that are still being pulled down by the force of gravity. So gravity pulls them down. And then Millikan was able to use electric fields to counterbalance the force of gravity, pulling them down. And with the electric field, by changing the polarity on the poles, because you've got a pole here that they fell through. So here's one. And then there's another charged plate, the negatively charged plates down below. Here's the positively charged plate. He can then look with the microscope, he can look and see and make that adjustment on the electric field to perfectly counterbalance the force of gravity and basically suspend these oil droplets in midair. And by changing it more, you can actually have it go against the force of gravity. In doing this, Millikan was actually able to separate out the charge value from the mass to charge ratio. So for Millikan's experiment, this is where we get the charge of an electron. So I usually use a lowercase e with a negative sign on top for shorthand for electron, because I don't like writing out the word every time. So the charge of electron, now we have it's 1.6 times 10 to the minus 19th coulombs. And because we knew what the mass to charge ratio was from Thomson's experiment, now we know what the mass of an electron is, which is about 9.1 times 10 to the minus 28th kilograms. That's really, really tiny. But it does have a mass, okay? In the context of the whole atom, and again, you got this from the video, the mass of the electron is so small relative to the mass of the protons and neutrons that it's pretty negligible. We don't even consider it, but it does have a mass, which is really, really, really small. All right, so now we have a little bit more information to build our model of the atom, although I haven't shown you what the model is yet. That really comes from Thomson's work. Here, I'll come back to the slide in a minute. Let me tell you about the model that Thomson used. Thomson's model from his cathode ray tube experiment is famously called the plum pudding model of the atom. Does anyone know what plum pudding is? Pretty gross, yeah. I mean, I've never tried it before, but when I read about it, I'm thinking, yeah, it's pretty gross, which is very appropriate name for this model too, because the model wasn't very good either. And the model was replaced probably within the next 10 to 20 years from the work of Ernest Rutherford. But first, let me tell you a little bit about the plum pudding model, because a model is good enough to explain the data that has been collected so far. And for the data that Thomson had in the cathode ray tube experiment, it was completely adequate. So it was fine for its time. And his model was building off of Dalton's model of this sphere of just stuff that was neutral. There was nothing in it. But now he has evidence for electrons. And the electrons have a negative charge, but he didn't know anything else about how those were distributed in the atom. So he just kind of put them randomly throughout the pudding of the atom. And the plums are like, they're really like dried up raisins distributed in this pudding. And that's how he imagined that the electrons were. And then but because the electrons as particles had negative charge, overall the atom was still neutral. So the positive charge that made it neutral had to come from the rest of the atom. But here it was very diffuse. It was distributed throughout the sphere. So the positive charge was very diffuse. Now, it's important to talk about the plum pudding model because Rutherford's data that we're going to talk about next actually tests this model very, very clearly. If you go back to the scientific method, you have a model, you then make new predictions, you have a test for that prediction. And with Rutherford's experiment, there were two clear outcomes based on either the plum pudding model or maybe something else is going on. But before I tell you about that, something else with the scientific method I want to add to, I'm always reminded of that when I see this picture. If you Google the Guild system, you'll get a picture that looks like this. So for all you history buffs out there, you know what the Guild system is? How you learn a trade? Anyone? No? The master and the, sorry, go ahead. Exactly, you're an apprentice of a tradesman. So here's the apprentice. And the tradesman is usually called the master. And then there's also something in between that I'm sure nobody in this room knows. So you've been an apprentice and you're on your way to becoming a master, but you have to go to some other masters, I suppose, and maybe do a little bit more work before you actually become a master. Anyone know what that's called? Go for it. It's what? Protege. That's a good name, but no, it's not. And maybe it is, but at least when I Googled it, that's not what I found. I found journeyman. Actually, I didn't find it. I remember learning this in the history class way back when I was in high school. A journeyman is kind of the in-between. But I mention this to you because in science, you have the same thing. The apprentice, this is you all right now. You are undergraduates. You're learning science with me now. You may, depending on what you do, join a laboratory here and start learning how to actually do science in the laboratory. So you become the apprentice and you're learning from the master, but you're also learning from the journeyman. This is the graduate student. They're going for a master's degree or maybe a PhD. And then you go off and you form your own lab, you get an academic position somewhere, do your own independent research. Usually that research is related to how you were trained as a journeyman, or maybe even how you were trained as an apprentice, or maybe you're going off to do something completely different. But either way, the master in the academic setting, this is what we call the principal investigator, or PI for short. So this is very appropriate for science, and it's appropriate for this story because it turns out that Rutherford was a student of J.J. Thomson's. So Rutherford did his graduate work in the laboratory that had developed this plum pudding model. Now, Rutherford went on to do his own research, mostly in radioactivity. Radioactivity and radiation. These people listed below Rutherford were either in his laboratory or were contemporaries, worked along with him. Maybe some of these names you recognize, like Marie Curie, all right? Very, very important scientist in the development of radioactivity. Becquerel and Roentgen, maybe don't know those names unless you study nuclear physics and nuclear chemistry. Rutherford had his own graduate students by the names of Hans Geiger and Ernest Marsden. Now, Geiger, you've probably heard of Geiger, right? Geiger counters, all right? So these folks were all working in radioactivity, but I guess Rutherford still had a fondness for his old master, and maybe he despised plum pudding so much that he decided to test that theory. So he sent Geiger and Marsden off to do some experiments that should test the model of plum pudding. Whoops. Test the plum pudding model. And they're going to do that with some radioactivity. Now, I brought this story up also to point out that it's very, sorry, let me start that again. Doing this experiment with radioactivity, we don't have time to really study a lot about radioactivity, but there are things that maybe you've heard of, like beta particles or alpha particles in radiation. And these are things that the labs were studying. So alpha particles, it turns out, have some mass. These turn out to be pretty much the helium nucleus. Meaning that they have 2 protons and they have 2 neutrons. But what's important about this, oh, they also are very, very high energy. These are both high energy particles that are emitted from isotopes that are radioactive. And in the process of undergoing radioactive decay, they become more stable. But what's important for this discussion is that these alpha particles have mass. They have mass, and they have a charge. What would the charge of these particles be? It would be +2, because protons have a positive charge, right? Electrons, we already know, have a negative charge. Now, they might not have known about protons and neutrons at the time, all right, but they knew that alpha particles had a mass and they have a positive charge. And both of those are going to be very important for us to interpret the data that they found in the next experiment, which is classically referred to as the Rutherford experiment, because it was done in Rutherford's lab. And Rutherford, probably designed it, maybe not, but interpreted it. But it was his students that actually did this experiment. And it kind of goes like this. It's very similar to the cathode ray tube experiment, except now we have a circular phosphorescent screen. So it's not just at one end of where the beam source is, it's all around. Now the beam source, in this case, is going to be those alpha particles, an alpha emitter. So alpha particles are coming out of here. Remember, these are high energy and they have a positive charge, right? They have mass and they're positively charged. Now, rather than draw all over the textbook's picture of this, I've got my own little schematic up on top. So here we have our alpha source. And we're going to look at a phosphorescent screen. Now, even though this screen is circular, I'm just drawing it as on the other end. And what they did, well, first, let's just see, the alpha particle is expected to go straight along, and when it hits the screen, it lights up, just like we had in the cathode ray tube. Now, instead of using electric and magnetic fields, they instead took a thin piece of gold foil. Actually, I should probably put that down below because this is the same thing down here. So now we're going to put some gold foil. And we've got some predictions from the plum pudding model of what happens when you shoot some massive positively charged particles through gold foil, given the plum pudding model of what's in this case, the gold atom. So let's take a look on the right here. This is going to be our prediction. Oops. The prediction of the plum pudding model. They're expecting that, so each black arrow now is one of these massive positively charged alpha particles shooting through the gold foil. When it goes through an actual gold atom, because of the plum pudding model, they're expecting most of them to just go straight through because the positive charge isn't really encountering a negatively charged electron there. Now you might think, well, wait a minute, don't same charges repel each other? Yes, they do. But we have a highly energetic, massive, positively charged alpha particle going through this sphere. Remember, the positive charge in the plum pudding model is that it's diffuse. It's all over the place. So really, whatever that positive charge is, it's spread out so much that you're not really going to get positive and positive repelling each other. So they're expecting most of the particles to pass straight through. Maybe on occasion, a positive charge will come close to a negatively charged electron, and so it might get deflected towards that that negative charge a little bit because opposites do attract. Right, so that's what's kind of shown here. Right, you've got one that's deflected just a little bit, but for the most part, they're going straight through. And when they did that experiment, that's pretty much what they found. They found that most of the particles went straight through and hit the screen on the other side as if nothing was there at all. Right, so that observation is consistent with the plum pudding model. In fact, they also found on occasion there was a little bit of deflection. Again, all of that is expected. Okay. So that was observed. But they observed other things that they didn't expect. In particular, they found that there was deflection more than expected And the big shocker was that once in a while, they found some particles that actually went backwards. And you can see that in the cartoon from the textbook on the left. That was absolutely not expected. This thin gold foil, it's literally just a few atoms thick. The plum pudding model had no way to predict or explain that these particles would run backwards. The result was so shocking that the story goes, I wasn't there. When Rutherford saw these results, it was so shocking that it was like taking a cannon, shooting a cannon at a piece of tissue paper and having the cannonball bounce back in your face. That's how surprising and shocking that this result was. Of course, as good scientists, they repeated it, scientific method, right? You got to refine your experiments and all that stuff to really make sure that your observations were correct, and they were. So now we need a new model. The plum pudding model was insufficient to explain how these particles could bounce back. So the new model now puts almost all of the mass at one centralized region or dense region of the atom that's called the nucleus. Okay, so this is what we call the Rutherford model. So the new model to explain the data. Okay, we have a very dense nucleus, and it's written down here, the nucleus region of concentrated mass and positive charge. Okay, so we have this dense, positively charged nucleus. We're placing it at the center. I don't know that there's any evidence in their data that suggested that the nucleus had to be in the center, as opposed to being on one side or the other. But you know, the center is nice. I like center. Things are symmetrical. And then they had the electrons, which still distributed somewhere in the rest of it. Okay. So there are so this is now, of course, we know about protons and neutrons. They're going to be in this dense, positively charged nucleus. And then we have the electrons here that are going to occupy the rest of the volume. Meaning that most all of the volume of the atom is empty space. And if you recall from the video, the volume of the atom, most of it's taken up by the electron, but the electron has almost none of the mass. Almost all of the mass of an atom is coming from the nucleus, but with this model, the nucleus is almost none of the volume. In fact, the gold atom, I should write this in gold. Oh, I don't need to. Sure, why not? The gold atom, the nucleus is approximately 1/10,000th of the volume. Just to give you a relative idea of the relative sizes there. Now, the model that Rutherford came up with to explain this, because models are very useful, right, looks something like this. You've got your dense nucleus in the center. And then, now remember, these electrons, all of the evidence so far has been that the electrons have mass, so they're particles. And so we're thinking, how do these particles exist in this atom? Well, Rutherford imagined that these electrons were in orbit around the central dense nucleus. And that's a picture of an atom that you probably recognize without me telling you that that's an atom. In fact, I think I drew that for you on the very first day, right? As you'll see, when we get into chapter 3 and beyond, this is not how we currently think the atom actually is operating, with electrons, particles in orbit around a nucleus like that. No, in fact, we'll see that we don't have orbits, but in chapter 3, we're going to do some quantum theory. We're going to find that we have things called orbitals. But this is going to be quantum theory chapter 3. We'll get there. Don't worry, I'm not going to talk about that now. But this model of the atom, the Rutherford model of the atom, even though it doesn't really describe how we think electrons are behaving today, is still very, very useful. You can see it on the banners outside the science building, okay? It still shows that the atom is mostly empty space, and that you do have electrons that are defining most of that space in not orbits, but in these orbitals, right? But that most of the mass is concentrated in the nucleus, which is at the center. It's dense and it's positively charged. Right, so this is the new model. It's called the Rutherford model. And although Rutherford didn't necessarily win the Nobel Prize, he did get an element named after him. If you look on the periodic table here, where is it? It's in there somewhere. Rutherfordium, something like that. There it is, 104. So you either win a Nobel Prize or you get an element named after you, or sometimes, if you're lucky, like Einstein, you get both, right? ES, number 99, Einsteinium. All right, so let's look a little bit more detail about the relative size. I told you that the gold atom, the nucleus, was about 1/1000th of the volume. But let's take this to another level to see if I can really impress upon you what this relative distance or relationship is. So let's say that the nucleus was a golf ball. So here's my artistic rendition of a golf ball. And let's say there's an electron out here, right, which belongs to that nucleus in some atom. Relatively speaking, right, if the nucleus was the size of a golf ball, how far away do you suppose that electron is? A couple light years? Okay, that's a little too far. Bring it in just a little bit. All right, it's about 1.5 miles away to get the relative distance between the nucleus and the closest electron if the nucleus was as large as a golf ball. Now, sometimes that comparison impresses students, other times it doesn't. So I have this other example here. Here's my beautiful drawing of the planet Earth that we all live on. So let's say that the nucleus was the size of the planet Earth. How far away is the closest electron on that relative scale? Well, here's an idea. I'm showing you the Earth and the sun. Anyone know what the approximate distance is between the Earth and the sun? Somebody always knows that number in class. What did you say?
96.
96. I think it's 93, but it depends, I guess, where you are in the orbit. Whatever it is, 93, 96. My notes say 93, so I'm not saying you're wrong, all right? But my notes say 93 million miles. This will still get the idea across. So we've got approximately 93 million miles between the Earth and the sun. That doesn't even come close to how far the electron would be if the Earth were the nucleus. To show you that, I have to do something that you can't do in your notes, but I like doing it on Notability here because I can always do that. I'm going to shrink it down. Smaller and smaller we go. Now, just to remind you, this distance here, this is still 93 million miles, okay? Times 10 to the 9th, that's million, right? 93 million miles. But I have to go even further. Let's shrink it down. Can you see it? Oh, you can still see it. Let's go even more. Can you see that? Little bit, you can still see it? Okay. Let's go down. It's still there. Probably what you can see now is that little marking that I made, right? Okay, that's fine. So you know that that's 93 million miles all the way there, right? You've got to go, where is it? Oh, here. You've got to go about 10,000 times farther than the relative distance between the Earth and the sun to get to the relative distance of the nucleus, if it were the Earth, and the closest electron. That's how far. Mind blown? Yeah, right? It's pretty far. Okay, so that gives you an idea of what we're working with here now. And we've spent some time looking at models and the scientific theory. Now in chapter 2, that's as far as we're going as far as model building for the atom. When we get to chapter 3, quantum theory, but that won't be until after the exam. What we're going to do for the rest of this chapter is spend some time looking at the periodic table and understanding a little bit about that. And then we're going to be looking at isotopes. So learning more things about protons and neutrons,